Okay, so for 41, explain why the coefficients in a balanced reaction represent not only molar amounts, but also relative volumes for gases. So Avogadro's law says that 1 mole of a gas, no matter what kind of gas it is, always occupies 22.4 liters. So because it doesn't matter what kind of gas it is, it always is the same volume. You can relate moles to liters in the equation. And so, you know, like an equation like this, where hydrogen gas plus oxygen gas goes to form water vapor. Balance it. This number can tell you how many moles are reacting. So we have 2 moles of H2 reacting with 1 mole, but also tells you that that's 2 liters reacting of H2 because of this principle right here.
Okay, that makes sense. Also, could you go over, 1 second, number 25C?
Okay, 25C. Go ahead and clear this. Okay, so we have 2HI. That should be aqueous. I forgot to write that in there. Reacting with ammonium sulfide. And that goes to form H2S gas. And then ammonium iodide. That's aqueous. Okay, so we'd split the metals from the nonmetals. H in front, that's acting like a metal. So we would get H pluses and then I minus. And then for the next one, there's no metals in here, but a polyatomic ion will act like a metal. So if you look on your chart, you're going to see this is ammonium. So ammonium will separate from the other part. So you'll have NH4 plus, and there's 2 of them. So put 2 in front of here. And then sulfur, -2 charge. And then the right-hand side, H2S is a gas, so that won't separate, so you just keep it as it is. And then same deal for this, NH4 is ammonium, so it'll stay together, so we have 2 NH4 plus, and then we'd have 2 I minus. So that's the complete equation.
How would you know to split hydrogen up?
Over here, like right here with HI?
Yeah.
So if it's H in front, then you can do that. Now, if it's an H in the back, then you wouldn't. So like right here with NH4, you don't, because it's not the first one. But if it's the first one, it acts like a metal in that case, and that will separate from the rest.
Okay, that makes sense.
And the reason why over here it wouldn't separate with the H2S is because it's a gas. But if that were aqueous, it would do the same thing, and you'd see H separate from the S.
So if it's aqueous, then it separates, but if it's a gas, it doesn't.
Right, and if it's a solid liquid, same thing, it won't separate. Only aqueous will separate.
Okay, that makes sense.
And the deal from there, you cross out. Actually, that shouldn't even cross out. So you'd have NH4 cross out. You'd have I cross out. And so then for net, you'd have H plus S2 minus goes to form H2 gas.
Could we also go over 43?
Sure.
Thank you.
Okay, for that one, it says to produce 15.4 liters of nitrogen dioxide gas, 310 Kelvin, 2.0 atmospheres. How many liters of nitrogen gas and oxygen are required? So we need to write the equation to start with on here. So reacting nitrogen with oxygen to produce nitrogen dioxide. That's NO2. Now, remember that these are diatomic. It's part of Hankel-Briff. And so if it's nitrogen gas on its own, it actually would be N2. And same thing with oxygen.
Why would it be that?
Oh, remember I told you before about this, that these
Oh, yes.
polyatomic ions, and so each of these would, if they're on their own, would be juice.
Yeah, that makes sense. Thank you.
So we would now balance it. So we put 2 in front of here to get 4 O's. We have 2 N's on both sides. Okay, so that's a balanced equation. And they're telling us that we have 15.4 liters of NO2 produced. And they're asking how many liters of nitrogen gas and oxygen gas are required. So we can use Avogadro's law to figure this out, where we said before that this can be moles or it can be liters. So what this can say is that you get 2 liters of NO2 produced for every 2 liters of oxygen and 1 liter of nitrogen. So the mole ratio we could say is for every 1 liter of N2, you get 2 liters of NO2 produced. And we can take what we've been given, 15.4 liters of NO2, and multiply it by this ratio. It'll cancel out NO2, and we get liters of N2. So that would be equal to 7.70 liters of N2 gas. And then they're also asking oxygen gas, so we do the same thing. You take 15.4 liters of NO2 and convert it to oxygen. And so that ratio we would have for every 2 liters of O2, you get 2 liters of NO2 produced. So that'd be a 2-to-2 ratio or a 1-to-1 ratio. And so we get 15.4 liters of O2.
That makes sense. One second.
Oh, sure, take your time.
So I know you went over 20, but I didn't understand how to do the shortest bond and the longest bond. I didn't get how you're supposed to figure that out.
Okay, look at 20 really fast. Okay, so for that one, if you go, I'll just erase this really fast. So we have HI, that's a single bond. CL is single. O2 is double. And then N2 is triple. A single bond is the longest and the weakest. So remember what a bond represents. It represents shared electrons. And this one right here, you could rewrite this as showing these 2 electrons being shared between the 2 atoms. That's what this bond means. So if you have a single bond, they're sharing 2 electrons. A double bond, you have now 4 electrons being shared.
Okay, I see.
Well, in order to share 4 electrons, they actually have to be closer than to share 2 electrons.
They're just stronger.
Exactly right. So let me kind of draw a little bit better that, that they're closer together. But every time they share more electrons, in order to share them, they have to be closer. So they get closer and closer with more electrons being shared. And then within, you're going to have 6 electrons being shared. So they have to be very close. In order to,
would be the strongest, basically.
Exactly right. So, and the closer they are, the stronger they are.
Okay, makes sense. But then how do you, if there's 2 short ones, because there's HI and Cl and Cl, how do you find the shortest bond between these 2 atoms?
Oh, actually, this would be the longest right here. So this would be the longest and the weakest. So because they're further apart, the more electrons they share, the closer they are. So a single bond is the longest and
I see, yeah.
the weakest bond, and they don't ask that, I don't think. They ask for the shortest.
So that would be N2 as well?
Yeah, so N2 is shortest.
And strongest.
Exactly.
Makes sense. And then how would you do the sigma and pi bonds on each of those?
Okay. So for that one, let me see if I can clear some of this off. It's just really memorization. Okay. So if you have, we'll just start with ClCl. When you have this overlapping right here, that's called a sigma bond. So when you have orbitals overlapping.
Okay.
And that's always for one single bond. So one single bond is always a sigma.
So Cl and HI would be sigma?
Exactly. It gets more complicated as you get to double and triple bonds, but for double bond, what you have, see if I can draw this. So we know that we have 2 shared electrons amongst the O, and that would be a sigma bond. But they share actually 4 electrons. If they have 2 bonds, they're sharing 4 electrons. So how are the other 2 shared? Well, they're not actually shared right here, and I showed you before that. That was just simplified version, but the electrons that they share, if it's beyond 2, would be in the p orbitals. So what you'd actually would see would be these p orbitals, and you'd have 1 electron here and 1 here, and they would be sharing it amongst the p orbitals. And that whole thing would be 1 pi bond. So these 4 lobes right here would make up 1 pi bond, where you have p orbitals overlapping.
Okay, I see.
Now you don't have to memorize the p orbital arrangement and what that looks like. All you need to remember is this, that if you have a double bond is always going to be 1 sigma bond, as we saw right here in the middle, and 1 pi bond. And that's what you always get with double bond, is both of those together.
All right, let me write that down real quick. So what would happen if you have 3 bonds, the triple bond?
Okay, so for that one, it's going to start the same way, where you have a sigma bond, and so that would be the first step. Then you'd have, like I showed you for the double bond, a pi bond coming off from the p orbitals. So they always build the same way. And so you have 2 shared electrons amongst that. So that gives you, so far, a pi and a sigma, and that's the double bond. For a triple bond, you're going to have an additional p orbital. It would actually be coming out of the board, which I can't really draw on here, but think of it coming out that way and into the board. And you would have, again, 4 lobes. And so the p orbitals will overlap with 4 lobes. You'd have 2 electrons being shared, and that would give you another pi. And so you would have for this one, 1 sigma and 2 pi bonds.
That makes sense.
And that's all you have to memorize. You don't need to recognize this diagram. You don't need to be all this, or remember that there's pi orbitals being shared. All you have to remember is this: that with double bonds you get a sigma and pi. That for a triple bond you get a sigma and 2 pi, and then single is just 1 sigma. That's all you have to remember.
Okay, perfect. Well, I think that's it. That's all I really had questions on. Thank you very much. I really appreciate it.
You're welcome. Have a good day.
You too.
Morning, Isabella. Do you have a question?
Yeah, I have a question on number 41.
Okay.
I understand how like the coefficients can represent moles, molecules, and liters, but I didn't know how to explain why.
Yeah, it has to do with Avogadro's law. And what he said is that 1 mole of gas is going to take up the same amount of space no matter what gas it is. It always will be 22.4 liters at STP. So because no matter what kind of gas it is, 1 mole is the same volume, you can relate liters the same way as moles.
Okay, thank you.
You're welcome.
And then do I just take pictures and send you my answers?
Yes.
Okay, cool. Thank you.
Have a good day.
You too.